This video is for the panel drilling machine detail overview. This is for Senior Design Project Team 12 for our sponsor, Koops Automation Systems. Koops' goal for this project is to help automate a process that is currently done manually by members of their team. This process involves the assembly of panels that sit inside of enclosures on automated machinery. The process of laying out and drilling holes for wireways and DIN rails is tedious and time-consuming. And so the goal of this project is to automatically collect and drill the layout for wireway and DIN rail inside of a back panel. Listed on this slide are the major specifications among the many others for our project. Specifically, our machine must accept a panel ranging in width and length of 16 to 72 inches. The machine must also create holes with a number 21 size drill bit with a tolerance of 0.01 inches. The machine must have software-assisted hole coordinate input, along with an emergency stop safety measures, and the overall budget for our machine is $14,000. Overall, the design that we have chosen to move forward with is a 2.5 axis CNC-controlled gantry-style drilling machine. That is a CNC machine with a servo-controlled x-axis, a servo-controlled y-axis, and a pneumatically driven drill. The software will use G-code generated from the electrical drawings and will be driven using the Acorn CNC controller. Overall, the machine has a length of 10 feet, width of 9 feet, a working height of around 33 inches, and this total covers 90 square feet of floor space. Overall, our extrusion frame was built from multiple sizes of 80/20 aluminum extrusion. These sizes include 15 series and 30 series extrusion. Around the outer edge, we have a 3x3 inch extrusion, and then throughout the middle, we get down to as small as 1.5 by 1.5 inches. It's estimated that our extrusion frame costs around $1,800. Moving forward in the assembly of our machine, we incorporated MDF board to create a smooth tabletop type surface for resting our panels. This sits flush with the inner portions of the frame and uses undermount aluminum brackets to hold those pieces flush. On top of the MDF board, we mounted a clamp system along with fence blocks. These fence blocks are used to create a common reference point for every plate that is put within our machine. This will locate our plate in the X direction and in the Y direction, as well as clamp it in place. Here you can see the 4 fence plates along the X direction. Alongside the fence plates is a simple swing clamp to secure our panel in place. We chose to go with a swing clamp because of its simplicity and the ability to fit it in a small area where we wanted it. Our swing clamp has a clamping force of around 120 pounds when fully engaged. On the left of these two pictures, you can see the swing clamp unlocked and disengaged. When moving the black handle in a clockwise fashion, the clamp is engaged and is able to lock down on top of the panel. Moving on to the X-axis actuation, on the top and bottom you can see 2 belt actuators, and then on the left side you can see a plate with guarding, and underneath that guarding are bearings and 2 shafts. We're using this system to time everything together and move our entire bridge back and forth without binding. Here's a closer up of the actuators we have installed on our machine. We specifically chose Misumi MSA SB1 series belt actuators. They have a length of 2,750 millimeters, They're simply mounted with corner brackets and have a repeatability of 0.025 millimeters. Driving those belt actuators are two servos and gearboxes. On the left picture here, we have the servo that is connected directly to the bridge and directly to the Z assembly. This is one servo driving one actuator to move our Z assembly back and forth. On the right, we have another servo and gearbox that is driving the shaft that we were previously talking about for the timing of the two belt actuators. Due to the weight of the bridge, as well as the length of the bridge, we chose to move forward with Roll-On Compact Rail Plus guiding system. This system is there to support the weight of the bridge while the Mizumi actuators move the bridge. Again, we have the gearboxes connected to the servos, which then drive the entire system. And then we have found that our timing pulley has a ratio of about 1 to 1.5 due to the 22 teeth and 34 teeth timing pulleys that we have chosen. Moving on to the Y-axis bridge assembly. On the left here, you can see the bridge as we were starting to assemble it. And then on the right, you can see two photos where it's assembled currently. One of those photos is how it fits on the machine while it's moved all the way into the 0 position. And then the lower picture there is how we have our servo mounted on. We will not be going into a lot of detail on this portion of the machine, as we've chosen to move forward with very similar design as the rest of the machine. Lastly, we have some pictures of the Z assembly. We are using a DeWalt drill that has a speed of around 2,700 RPM. We have two small clamps that clamp onto the collar of the drill along with the body of the drill. And then the entire assembly is being actuated using one pneumatic cylinder with a stroke of about 2 inches. At this point, we will move on to the software design of our project. As previously mentioned, the current process of drilling these panels is done by hand and manual measurement. Our solution involves creating readable G-code for our CNC controller. To accomplish this, the electrical schematic must be exported from ePlan and modified in SOLIDWORKS, where macros can be applied.
The purpose of the macro is to generate G-code for the machine to give the location of the drill holes that are necessary for the panel. To do this, we need to know the panel's layout. Koops makes their panel layouts in a software called ePlan. Unfortunately, because of licensing restrictions, we cannot manipulate or read data from ePlan. So we export their plan as a DXF and open that in SOLIDWORKS, which is what you see right here. So you can see some wireways, you can see the components for this panel, and so on. So you can see that there are a lot of unnecessary layers, and we still have the components in here. So the first thing that the macro will do is simplify the panel layout. So it's going to delete these extra layers, and then it's going to delete any line shorter than the wireways width we're looking for. So we're looking for these, but anything shorter than those we're going to ignore. So it's going to delete. So let's go ahead and start our macro. So you'll see it's going to ask me to browse and find a file. So I'm going to go to my test files. It's going to open up. It's going to look exactly like it does behind me. So this is the direct file exported from ePlan. So I'm going to hit done. It's going to first delete those extra files, or those extra layers, and then it's going to ask me to make the sketch editable so that we can delete those unnecessary lines. So the reason this is necessary is that a lot of these extra points, it will take the macro much longer for our sorting algorithm to work. So the way the macro is going to work is it's going to look at each lower hand left corner of a wireway, whether horizontally or vertically applied. The next thing it's going to do is look if there's a point in either of those directions that is a expected width away. So the 1.25, the 3.25, etc. It's going to see, okay, I have one here, so I'm going to check for my other 4 corner points. So it's going to look for matching coordinates, and it's going to see those. It's going to do the same thing for the horizontally ones. So it's going to need me to enter in the panel width and panel height. This is so that any points outside of the expected panel that are left over, so sometimes you'll see there's an extra set up over here with a couple other wireways that we don't want to include, so it's going to ignore everything outside of these things. So this is a 17 by 17 panel, so that's the only points we want to consider. So you'll also see that this is not, this point, the origin is about here right now, so it's also going to move these wireways over to the origin. So after this, it's going to delete the original drawing, and it's going to recreate each of the wireways. So you'll see this momentarily. So here we go. It's going to recreate each of the wireways, and then it's going to go through each wireway that's not been modified yet and make the drill pattern based on the width and the length. So you're going to see this pattern continue for all of these. If it's one of the wider wireways, it'll be 2 rows, and you'll see an alternating pattern. So it'll go the it'll do the 4 available corners, and then it'll do an alternating pattern for the ones in between. For the single row ones, it's going to do every 4 inches. And then 2 inches from the factory edge, which is either the left-hand side or the left-hand side here, or the top side. From here, the macro will open SolidWorks CAM. It's going to extract machinable features. Once we do that, we're going to generate the operation plan, generate the toolpath, and then generate the G-code. So currently, this part of the macro is still being developed, but that is what they will do. This process has already been worked out, and we have some sample ones ready to go. But that is what the macro will do. So once that G-code is generated, it will be transferred over to the machine, and the machine's controller can go from there.
The panel build machine is controlled by the Acorn CNC controller from Centroid. The controller has several relay outputs, as well as inputs. The Acorn CNC controls the position of the machine based on G-code commands from the CNC computer. Most of the inputs consist of proximity sensors, which detect the position of the machine. And the outputs consist of servo motors, the Z-axis cylinder, and the drill.